Okay, in this video, I would like to demonstrate a simple thermal comfort CFD simulation using tensorHVAC-Pro, which is a dedicated flow and thermal simulation software for HVAC application. And the software is designed for intuitive and easy to use for HVAC designer, not for CFD expert. Okay, without further ado, let's jump into it. First, let's make your project name. Let's say cafe trial YY, I don't know, just make it your name. Then browse the project path, which the folder or directory you want to save your project. Let's create the case, and for the geometry we will import it as the from the STL format, which you can easily export from your Revit or your SketchUp if you are architect or maybe civil engineer, or from SolidWorks or Autodesk Inventor if you are mechanical engineer. And this STL, maybe I will also give you the access to it in the link in the description below. And yeah, this case I will show you by hiding this ceiling is just a very simple cafe with 3 occupants in it, with some chairs and also tables and a coffee maker. And we have air conditioning unit here to be simulated, and to make sure that all the occupants get satisfied with the thermal condition. Okay, let's define each object here by selecting this boundary condition. So inlet is basically where the surface, or like a place where the air comes out from the system. Let's say for in this case is in this surface of this indoor unit, or if you are using diffuser from our air conditioning unit, that will be the inlet. And for the outlet is the place where the air sucks back to the system, and we will use this top surface as the outlet. And object and also wall are basically essentially the same. The difference will be just on the mesh resolution. If you select this part as an object, it will have better resolution. Okay, let's define it one by one. Object, and for ceiling we will use the wall. Chair is object, coffee maker is object, floor, wall, and the human of course are objects. The inner unit is object, and the wall is obviously wall. Okay, from these STLs we don't have the inlet and outlet yet. Basically you can generate it from your 3D modeler by creating some dummy surface or something like that. But if you don't have yet, don't worry, you can split the face here, let's say by just clicking the indoor unit and click this face as the inlet. And we will do the same thing for the outlet. Here we go, and we define the inlet as the inlet obviously, and the outlet as the outlet. And just update the mesh. You don't have to worry much about this mesh resolution. Basically the coarse mesh will create coarse resolution of mesh, which makes your simulation faster, but the resolution will be low. On the other hand, if you use fine mesh, the resolution will be better, but the running time will be longer. You actually can check the mesh, you can simulate the mesh resolution by using the wireframe here. you can check the different setup here, but let's just go with medium. Okay, the simulation, the meshing process is done. You can actually check the mesh on ParaView if you like, but it is not mandatory. It's just to make sure that your it's just to make sure that your mesh is finished properly, so we don't left anything error here. Okay, let's move on to the next step, which is the boundaries. Here we want to define the air flow from this air conditioning unit to the Z direction, and if you like, you can also tilt it down a little bit to the -Y direction. So let's define it, let's say 0.4 and 0.1 minus in the Y direction. These values you can refer to your own units manufacturer, or maybe you can calculate from the CFM if you have, using this calculator. And for the temperature, let's set it to the 20 degrees Celsius, or you can change the unit if you like to Fahrenheit, to Kelvin or Kelvin. For the wind, we will not use it because it's just like internal flow. And yep, for the object and the wall, we basically have three options for the temperature. First is driven, which is basically, the temperature will be driven by the outset, by the environment temperature. Let's say if you have object standing in environment condition with 30 degrees Celsius, the object will be also have 30 degrees Celsius, or it has some specific gradient, the gradient will follows that environment. For the T input, of course, is just the fixed value of the temperature, or if you like, you can also input the gradient, which is calculated from the heat flux and also the thermal conductivity. So let's say if we use human here, human has some specific dissipation heat from its metabolism process, so we can input some values and we will discuss these values later. Or if you like, you can check here, click here to get some reference on some of the typical values. Yep, we will discuss this later in detail. And human standing has a larger temperature gradient because it has faster metabolism rate. Okay, for the walls, let's say we have ceiling with get some radiation from the sun, which creates also, which reduces by the insulation system, let's say. Just put some random values here. And for the floor, we just keep it as driven, and for the wall, let's say it's like 35, I don't know, just put some random number. And again, this value will be different if you are simulating this simulation maybe during winter or summer, or maybe morning or night, or during the day will be different. So yeah, you have to check all of those scenarios. Okay, don't forget to update the mesh, and let's go to the next step, which is general setup, like the initial temperature. It doesn't matter, it's just like to guess the first temperature that will be in the room before you turn on the air conditioning system. And the comfort calculation, like the clothing, metabolic rate, and also relative humidity, we will discuss later on specific thermal comfort standards. Let's say for ASHRAE or ISO, they will have some specific parameters that we use to evaluate the comfort level. You can also check this link if you want to read the reference. Okay, let's go to the last step, which is solver setup. The end time is basically how many iteration will be done during the simulation. The more complex the case, more object there, more inlets, you need to have a larger number of end time, like 10,000, let's say. But if you have just like small room without object in it, maybe you need like only 1,000 iteration. But again, you need to do some trial and errors until you get the best end time. Maybe in this case I will use 5,000, and let's check later it is feasible or not. For the right interval, basically this is like 5,000 divided by 100. So every 100 iteration you will save your simulation, and in this case we will divide 5,000 divided by 100, which is 50 data. So you will have 50 data on your ParaView. And the parallel running, this is the number of cores. If you have more number of cores, your simulation will be faster. But again, the number of cores is limited by your hardware. If you have expensive hardware, let's say, maybe your number of cores will be higher, so your simulation can be faster. But if you use or utilize the whole cores in your system, you will slow down your other process. Maybe if you are rendering animation or rendering video, which is core intensive activity, maybe you have to reduce a little bit these cores. But again, it's up to you, the utilization of the cores. And yeah, I think that's all. Don't forget to update the setting, and let's start the simulation. For this kind of project, maybe it only takes a couple of minutes, or maybe for this case it takes around 15 minutes to 13 minutes, depends on your mesh resolution and also the number of core. And this is just the logs, so you can see if anything goes wrong, like errors display. You can easily find the troubleshooting in the discussion forum. Okay, after a couple of minutes we finally finished the iterations. You can see here the residual, which is basically just the zeros after comma. If you have 1 to the power of -5, it means like 0.0001. So the lower the value is better. And if the curve going flat, it also indicates that your simulation is converged, so it will not change with respect to iteration anymore. So okay, let's find out what is happening inside the simulation with ParaView. Here we go. This is our simulation result. You can change the time to the last iteration, which is 5,000. Here you can see that we have every 100 iterations here. This is just to make sure that your data doesn't change with the iteration anymore, so you can check. Yeah, it is almost the same value, so yeah. Okay, this temperature is still in the Kelvin unit, so let's convert it to Celsius by using this calculator. Let's say we want to calculate the temperature. We just name it T Celsius, and the equation is T minus 273.05 or something for Kelvin. Here we go, temperature in Kelvin. But yeah, we cannot see what's inside this object, so let me create a slice. So here we go, let's slice it right here. Maybe to make the visualization better, I will display the cafe trial but with solid color and wireframe. So here we go, we can see the section view here with our wireframe. Here we go. This is the temperature, and maybe we can make another slice in the Y direction or Y normal by click the calculator again and change the slice to the Y normal, adjust a little bit, and here we go, our temperature distribution. Or if you like, you can change this legend range by using this rescale to custom data, let's say 232, let's say, or change this lower value. Or you can automatically detect the minimum and maximum to the rescale to the visible data. Okay, this is the temperature. We can also check the data such as velocity to see how fast the speed of air around our body. Or we can explore another specific parameters like the DR or draft rate that we will discuss later on a specific video. And PNV and also the PPD are special parameters that often used in standards like ASHRAE or maybe ISO, which again we will discuss in the more detailed video. And for the H, here we can see the blue is indicating the fresh air, and red indicates the like air that's already been in this room since a while. And yeah, you can explore under another values, creating streamlines, or maybe plot some specific values, or maybe plot some the temperature of a body, let's say. Let's see here. For example, let's change the selection to the object 9. I'm not sure which one. Yeah, which is the human body, and you can plot the temperature here, for example. Yeah, you can explore anything you like, and maybe we will discuss the detail of how to do the proper post-processing in the different video. I think that's all for this video. You can comment in this comment section to ask about if you have any question related to this video, or if you have any special topic or request that we want to discuss. And you can also try this software for free that I will give you the link in the description below, so you can explore the capability of this software before you purchase the license. And I think that's all. Thank you for watching. See you in the next video.